Okay, let's get started. We're looking at the Gibbs Free Energy of a system. It's the new state function. We've already looked at internal energy, we looked at enthalpy, and we looked at entropy. The Gibbs Free Energy is a defined function. G is H minus Ts. And let me highlight my screen, my cursor a little bit. So this is the way the Gibbs free energy is defined. G is H minus Ts. And the Gibbs free energy defines a driving force for spontaneous change. Remember we said if delta H was negative, that is the system transmitted energy to the surroundings, or if the entropy was increasing for the universe, then that was a process that would become spontaneous. Both those driving forces. The Gibbs free energy uses both of those, but they're combined in a way so that we're only focusing on the system, the entropy of the system, not the entropy of the universe. But defined this way, delta G for a process will be will predict when the process is spontaneous. If delta G is negative, it is spontaneous. If delta G is positive, it will not happen by itself. The focus on spontaneous change is because these are the ones that can do useful work for us. Now, what do we mean by useful work? Actually, isn't all kinds of work useful? Well, there's a component of the work that just has to do with the change in volume when we go from initial state to final state. For example, if I had 6 moles of gas in an initial state, reactants, and it went to the final state, products, but there were only 3 moles of gas present, if the pressure is constant, then the volume will decrease during the reaction, which means the surroundings would compress, would come inward, and that would cause a work to be done, but it's not a useful part of work. That PV work just has to be done to go from state 1 to state 2. What we're interested in is the work in addition to that, and that's what the Gibbs free energy function does. If the decrease in Gibbs free energy for a process in a system is equal to the maximum amount of useful work that you can do. Wouldn't matter how much you could you actually do. When you calculate delta G, it gives you the maximum that you could do. And what you actually do could range from 0, no work at all, up to this value of delta G. Remember when we talked about delta E? We said that if you carry out a process at constant volume, that is in a rigid bomb calorimeter, then no work gets done. So the heat flow in that case was directly equal to delta E. Since that is one way of doing that process with no work being done. Now, if you carry it out in any other way, you might get some work done. But the maximum you could get would be delta G. So what is actually going to happen is you're going to get a heat flow somewhere between 0 and delta G. Now, temperature does affect the spontaneity of some processes. Looking at this Gibbs-Helmholtz equation up here, delta G is delta H minus T delta S, you can see if you change the sign of delta H and delta S, you can change the spontaneity of the process. If delta H is negative, then this first term is negative. If delta S is positive, then the second term is also negative. So delta G is going to be less than 0 no matter what the temperature is. So the process is spontaneous at all temperatures. Now, suppose delta G is greater than 0. So this term is trying to keep it from being spontaneous. If delta S is also greater than 0, then as the temperature goes up, the T delta S negative term gets more important. So it becomes spontaneous at high temperatures. You get the temperature high enough, the second term will overtake the first one, and then at that from that temperature on up, the process becomes spontaneous. Suppose you had delta H less than 0, so this term is negative, and delta S is less than 0, it's also negative. Well, if delta S is negative, that negative times that negative is positive, and delta H was less than 0. So at some low temperature, this term would become less important, and it would become spontaneous then at low temperature. So, and the other possibility is delta H is greater than 0, and delta S is less than 0. Then delta G would be greater. I think this is a duplicate of what we did earlier. But if delta, let's see, if delta H is less than 0, this term is negative. Delta S is less than 0, this term is positive. So this negative and this one positive would become low temperature. So I think these are predicting the same thing. Gibbs free energy must be defined relative to a standard state. Now, here's what we have this idea that there is a true 0 somewhere, and we don't know what it is, and we don't know how to configure a system that would have 0 free energy within it. But we can imagine that there must be some kind of configuration that would work, because if I started out with some value of delta G, I could imagine reducing it and reducing it and reducing it. Eventually I'd get to a 0. So I don't have any idea how to configure a system that has 0 true free energy. But if I did, I could go from that state and the free energy would go up, and I could go to state 1 and it would go up to that value, and then I could go to state 2 and it would go up to that value, and then state 2 minus state 1 would give me the delta G for the process. So there's state 2. We subtract off state 1. What we're left with is this much change in energy and going from state 1 to state 2. So this is relative to a true 0. Now suppose we did the same thing though, but let's imagine there is some configuration up here that we could call a reference state, and we just say that that's 0. Okay, well, then I could measure the distance from that 0 state that we can define up to this state, and that would be the free energy for state 1. Then I could go and measure the energy to go from this reference state to state 2, and then I could take state 2 to state 1. State 1 to state 2 would give me the delta G for the process. So I would take state 2, a value, and I'd subtract off state 1, and you see I'm left with the same distance that I did with the reference state or with the true state. So delta G is independent of the reference state. We can define it any way we want to. But we do define it in a way that is convenient for us. As chemists, the most convenient reference state would be for us to take the elements in whatever state they're in at 1 atmosphere pressure and 25 degrees, and that we would call that configuration a 0. So anytime I've got an element, like for example, oxygen is diatomic and gaseous. So anytime I see O2 gaseous, that's a 0 for the reference for the free energy for that element in its standard state. So that's how we define the standard state in that way. Now, let's look at another consideration, and I've never seen textbooks do this right. They always say the standard state is 1 atmosphere pressure, but they don't distinguish the fact that when you've got a mixture of things, each one of them has to be at 1 atmosphere pressure. Here's a reaction, N2 and 3H2, all gaseous, going to 2NH3 gaseous. So this is a reaction for the formation of ammonia from its elements. And the standard state of that would have each of the elements, each of the substances present at 1 atmosphere pressure. So the partial pressure of N2 in this standard mixture is 1 atmosphere. The partial pressure of H2 in this standard mixture is 1 atmosphere. The partial pressure of ammonia in this standard state is 1 atmosphere. The total pressure by Dalton's law is the sum of the partial pressures. So it's 3 atmospheres. From Raoult's law, you can get the mole fraction of any component is just its partial pressure divided by the total pressure. So the mole fraction of each gas is 0.333. Now, this is the important thing about the standard state. It defines a particular set of concentrations that you have. Those are not the concentrations maybe you're doing in the lab. For example, if I'm carrying out that reaction with nitrogen and hydrogen to make ammonia, I probably don't start out with any ammonia in the system at all. That's my laboratory system. That has nothing to do with the standard state. The standard state is 1 atmosphere partial pressure of each one, and the standard state is this fixed set of concentrations. That's critical. Be sure to understand that the standard state for a reaction is not 1 atmosphere total pressure in the lab. It's 1 atmosphere partial pressure of everything that's gaseous in the reaction. Now, if I look at what happens to free energy as we go from one state to the other, let's see, I need to go here. Okay. And now, this gives us an idea that we need to remember. There is a standard state. The standard state is defined as the elements in their natural state at 1 atmosphere pressure and 25 degrees Celsius or 298 Kelvin. If we're involving compounds, it's going to be at 1 atmosphere partial pressure for that compound at 25 degrees and or 298 Kelvin. And the standard mixture then is defined by the reaction and the number of moles of gases that's present. In general, the mole fraction of each component is 1 divided by the total number of gaseous components. So when you get a process to be at equilibrium, and I do want you to notice that I'm looking at 2 different ways of writing delta G. Delta G with the little superscript at the top right means it's in the standard state values. The delta G without the little superscript means it's whatever reaction mixture you have at this moment. So the delta G without the superscript refers to laboratory conditions. The delta G with the superscript is that hypothetical defined standard state. The delta G will be 0 when the process is at equilibrium. And at that point, if delta G is 0, the relationship between delta H and delta S is delta H is equal to T delta S. This is the temperature where equilibrium occurs, and we can calculate that if we know a value of delta H and delta S. The free energy of a mixture is defined by the composition of the mixture. For example, if I had ice and water mixed together, the free energy would be lowered if the mixture is changed to water at 25 degrees. So at any temperature less than or greater than 0 degrees, you will get the ice going to water. That's the spontaneous direction for an ice-water mixture at at any temperature above 0 degrees. Below 0 degrees, the free energy will be lowered as the water is changed to ice. So you see the equilibrium temperature for melting is 0 Celsius or 273 Kelvin. And that determines the place where the mixture of ice and water is stable. You can have any possible mixture of ice and water together, 50% ice, 50% water, or 10% one and 90% the other. It's going to be 0. At 0 degrees, all possible mixtures have the same free energy. So the system is just sitting there stable. Nothing's happening to it. So we want to go to the minimum free energy, and let's look at this cartoon. Here's a reaction. It's just a hypothetical reaction. I put a whole bunch of stuff up there, 2 moles of A and 3 moles of B to go to 4 moles of C. Now the Kp I defined as 0.5. Now what that would mean is I would take the partial pressure of C and raise it to the 4th power and divide it by the partial pressure of A squared and the partial pressure of B cubed. And if I did that and put in equilibrium partial pressures, the number I would get would be 0.5. Here are some numbers on the left showing the Gibbs free energy. As we change from this axis is 100% reactants. That's over here with only A and B present in the mixture. When I get over to 1, fraction reacted is 1, it's 100% reacted, then the mixture is only C. So if you go from only reactants to only products, in this case, these are the points that you would reach in going from reactants to products. I could draw a curve through that like that. Now, at 1/3 reacted, that means I've got 1/3 of the moles present is A, and 1/3 is B, and 1/3 is C. That is the composition of the mixture, and that represents the standard state of that mixture. If I'm over here and I'm saying I'm going to the right, reactants to products, then the delta G is greater than 0 going in that direction. It's not going to do that. It's got to go the other direction. And if it goes in the direction the arrow is showing, then sure enough, take one of these values and subtract off one of these values, you will get a negative number. So the spontaneous direction is back toward this value, this little orange point I'll make just now. That's where the delta G is equal to 0. It's tangent to that line at that point. And the delta G is 0 at that point. So this is the equilibrium place for this reaction. And then I would, that would give me the minimum free energy is where equilibrium takes place. And then if I'm looking at the delta G going in this direction, if I'm going again from reactants toward products, the delta G is going to be less than 0 because this value is smaller than this one. So final minus initial would give me a negative number. So if I'm on this side of equilibrium, I go toward equilibrium. If I'm on this side of equilibrium, I go toward equilibrium. Reactions always go from wherever you are toward equilibrium. The sign of delta G can be used to predict whether a reaction is spontaneous from where you are. Remember, I'm looking at delta G without the superscript. And it can be used to tell you whether you've got a spontaneous reaction. If you started with the standard mixture, you can go there as well. Because if you get delta G superscript equal to 0, then that means starting at the standard state, if delta G superscript is equal to 0, you're at equilibrium. But if delta G superscript is negative, then it will go further to the right in achieving equilibrium. If a process is not spontaneous in one direction, it is in the other direction. Remember, for any of the functions, if we reverse the direction of the reaction, we change the sign of that state function. So if it's, okay, let's look at some problems. Here's the reaction. It involves 2NO gas plus O2 gas to make 2NO2 gas. And we're to define the standard state, calculate delta G superscript, delta S superscript, and delta G superscript for that reaction. Now, let's look at the standard state. What does it say? Okay, it says that I have 1 atmosphere pressure of each gas present. That means the partial pressure of the NO is 1 atmosphere. The partial pressure of the O2 is 1 atmosphere. The partial pressure of the NO2 is 1 atmosphere. By the way, irregardless of the balancing coefficients. The total pressure is 1 atmosphere. So by Raoult's law, the mole fraction of each one is going to be 1 divided by 3, or 0.3333. Now we can use the tabled values to calculate delta H for the reaction. It's the delta H of the products minus the delta H of the reactants. And so we have 2 times the delta H of formation of the NO2 minus 2 times the delta H of formation of the NO. Now we leave off the oxygen because it's in its standard state. It's 0. If you look for the delta H of formation of O2 gases in the table, it might not even be listed, but if it is listed, it'll be listed as 0. Okay, we can plug in the numbers. The value of delta H of formation of NO2 is plus 33.84 kilojoules per mole, and there's 2 moles. So when I multiply that out, the unit's just kilojoules. If I take the delta H of formation of NO is plus 90.37 kilojoules per mole times 2 moles. Do the math, I get minus 113.06 kilojoules. Does that make sense? Well, the number looks okay. The sign, what about it? Well, it's an oxidative reaction. So oxidation reactions are almost always negative. In fact, I think they all are. I don't know of one that's not. Then the sign ought to be negative, and that's what we're observing. Now let's look at the entropy. The delta S is going to be the 2 times the third law entropy of NO minus 2 times the third law entropy of NO. I'm sorry, the first one was NO2. Minus the third law entropy, 1 times that of O2. Remember now, entropy does have an absolute value. All the rest of them are relative to a standard state, but not entropy. By the third law, the entropy is 0 when the temperature is absolute 0. So we have a well-defined 0 for entropy this way. And by the way, we can use that as a way of defining what we mean by absolute 0. Absolute 0 is the physical state you reach with no disorder at all at t equal to 0. So we can use that way of defining the third law entropy, and we can use the other way we defined it back earlier was using Charles' law. We saw that when the volume of the gases, when the volume went to 0, that would define absolute zero. We start cooling gases down. You would cool and cool and cool. As you cool them down, the volume gets smaller and smaller and smaller. And absolute zero is the temperature that would be required to make the gases have zero volume. The third law allows us to equate those two definitions. So whichever way you define the temperature, either by disorder going to zero or volume going to zero, you reach the same value for entropy. The entropies now, be careful, they're given as joules per mole per Kelvin. The unit on entropy is Q, joules, divided by T, temperature, degrees, K. So for NO2, it's 240.45 joules per mole per Kelvin times 2 moles, would give me joules per Kelvin. And then minus twice the NO value is 210.62 joules per mole per Kelvin. Again, times 2 moles is just joules per mole. And then the oxygen value is 205.0 joules per mole Kelvin. And when you do the math, you get minus 145.34 joules per Kelvin. And now, does that make sense? Well, let's look at the reaction. It goes from a disordered state that has 3 moles of gas in it to a more ordered state that only has 2 moles of gas. So the entropy does decrease, so it is negative. That makes sense. And now delta G is delta H minus T delta S. So we can plug in either the values we've just calculated, or we can get the delta G from the free energy formation of products minus reactants from the table, just like we did delta H and delta S. Most tables have all 3 in them. So if I use the method by taking these 2 values we just calculated, be careful. Remember that delta H and delta G are in kilojoules, whereas entropy was given in joules per mole. So I had to do the conversion to convert the 145.34 to 0.14534 kilojoules. And then I can do the math. If you do that, you get minus 69.75. And we would have to decide whether that's spontaneous to see if that sign makes sense. Well, I think it does because it is an oxidative reaction. Most oxidations are spontaneous. So delta G ought to be negative. Now, if I use the heat of formation of products minus reactants, I take 2 times 51.84. That's going to be for the NO2 minus twice the 86.71 kilojoules per mole for the NO. Notice there is no delta G of formation of oxygen. It's in its element. It's in its standard state. So I get minus 69.74. Well, that's pretty close agreement. I wouldn't expect that to be happening often. Now, will a mixture, 1 atmosphere of NO, 1 atmosphere of O2, and 1 atmosphere of NO2 proceed to the right or to the left in achieving equilibrium? Which direction is spontaneous? Well, this is the standard state. So we can look at the sign of the delta G, and it was negative 69.74. Delta G superscript was minus 69.74, which means it will achieve equilibrium going on to the right from that mixture that's 1/3 NO, 1/3 O2, and 1/3 NO2. It is spontaneous to the right. Now, will the temperature affect that reaction? Well, we can look at the Gibbs-Helmholtz equation again to get what's going to happen to delta G as we change the temperature. So if you look at that, we've got delta H was minus 113.06 minus T times minus 145.3. This second term is positive. So I've got a negative value plus a positive value times T. So you see, if this temperature is low, then it would be spontaneous, but if the temperature got very high, it would not be. So at 25 degrees, it becomes less negative as the temperature goes up. So its standard value is 25 degrees. If we increase the temperature above 25, certainly, it will be less negative. So it gets less favorable as you raise the temperature. Calculate the delta G at 100 degrees. Well, delta H and delta S don't change much with temperature. Delta G changes linearly with temperature. So all we have to do is use the delta H and delta S values we got from the table, and we can estimate then the delta G at some other temperature. Namely, I plug in these numbers and the new temperature at 373, and we come up with minus 58.85 kilojoules. Notice it is less negative than it was at the 25 degree value. So it did become less negative as we raise the temperature. Now there's a checkpoint on this. It's very much like the one we've done. It's a little more complex. You've got 4 reactants. They're all gas and products. They're all gaseous, so be a little careful. Here is the table of data for all of the substances involved in the reaction. And you can calculate delta H from summation of the products minus reactants. You can calculate delta S the same way from the middle column on the table. And you can calculate delta G also from the column on the right in the table in the same way as we've done before. And then use these top 2 values, delta H and delta S, and the Gibbs-Helmholtz equation to calculate delta G from those values. Remember, it's at 25 degrees there. What would be the mole fraction of Cl2 in the standard mixture? Now be real careful. I've kind of used examples all the way where that was 1/3. It's not going to be 1/3 in this one. Will the mole fraction of Cl2 increase, decrease, or not change in reaching equilibrium? Well, if you predict the reaction is spontaneous to the right, then it would increase the amount of Cl2 in the mixture. If you predict the other direction is spontaneous, then the amount of Cl2 would decrease in reaching equilibrium. And then will the reaction be more or less favorable at 50 degrees Celsius? Remember, table values are 25. You can calculate the new value at 50 and make the comparison. So this is very much like all of the stuff that we have done in the lecture just now. So you can go through, be sure to work these checkpoints out. If you're having difficulty with them, I would really like you to go into the discussion group and discuss it among yourselves. Ask your partners in this class what they got and how they got it, and then you all can come to some kind of agreement whether you think it's right or not. And then if you can't agree among yourselves, then email me. I check my email several times a day, and I'll be glad to try to answer your questions when I can. Now, on Monday, Wednesday, and Friday, I have lectures, and it takes most of the day up. My best day to answer emails is Tuesdays and Thursdays. Generally, I'm doing lab grading and some other things, or grading your papers if we've had a quiz or exam on those days. Okay, I hope this lesson made sense to you. If you have questions, feel free to email me, and we will go from there. Okay. All right. I'm recording this email, so this lecture. So I will end it now, and then we will post the transcribed video on D2L when it completes. All right. See you later. Bye-bye.